Hello and welcome to this video on finding the domain of a function. Now this video I'll preface by saying is intended more for the beginning / intermediate algebra crowd. I'm going to be given a function. I'm just going to do several examples where I'm given a function and asked to state its domain. But really nothing too crazy. We're just going to be determining whether or not we divide by 0 ever. So there's no logarithms or radicals involved in this video. So if you're looking for things on logarithms and radicals and finding the domain of a function involving those, I'll be doing one in the future. I'm sure about those, but you can look up other people's videos on those. I'm sure they're out there. Okay, so let's get into it. Alright, so just got a few examples for you here today. So the first one here, I'm asked to find the domain of each function. We've got several examples. Alright, so I'm given this function called f, right? I have a function notation here, f of x equals and then 3 times x squared plus 2. Where if you remember a little bit about the notation, what all this means is that my variable x, right, the x in there is the input value or the independent variable. So x is input slash independent variable. And this notation here is the value of f, this function we're calling f at x or f of x, and over here is how a value from the domain, how an input corresponds to a value in the range, right? How we take a value in the domain and calculate its corresponding value in the range, right? So x is the input, and then f of x itself, the whole thing, that entire thing represents basically the output, or sometimes it's interchangeable with the y coordinate. Might also just be called y, but this is the output slash dependent variable. All right. And when we're talking of domain, right, the domain of a function, I've mentioned this in videos before this, if you've seen any of my videos on functions or relations even, right? The domain is the set of all the inputs in a relation, right? And if and for a function especially, a function, the definition was every value of the domain corresponds to exactly one value of the range, right? And the range is the set of all the outputs. But I'm only asked to find the domain here, right? So when we're given a relation described as an equation, okay. So given a relation or given an equation for some relation, some function, we're going to assume that the domain is any real number that corresponds to a real number output. Right? Any real number, or anything on the real number line, and in most cases that would be the x-axis, and the y-axis represents possible values in the range. But any real number that corresponds to a real number output. Or corresponds to a real number in the range. All right, and again, the reason we're I mentioned earlier, this is more geared toward beginnings intermediate algebra, where for the most part we're dealing with the set of real numbers, and when we make graphs of relations, typically it's on the xy plane, where the x-axis is a real number line that's horizontal, and the y-axis is a real number line that's vertical. So if we want to make a graph, we can't plot the imaginary numbers, or we can, but as I said in the beginning intermediate algebra course, typically the imaginary numbers or non-real numbers are not plotted, not graphed. You only deal with sets of real numbers, so we're very restricted here. Alright, so things to look out for. Now in this video we're only going to worry about one thing. And the one thing we're going to look out for is you can't divide by zero. Right? Division by zero does not result in a real number or a real value. Division by zero is undefined. All right, so I'll say you can't divide by zero. Alright, so if there's ever a denominator with a variable in it, I'm going to try to determine, are there any values, any inputs, any arguments I could plug in that would make this denominator zero. If there are, then that value that I plugged in is not a part of the domain. This will be added to later. Okay, other things that that don't produce a real number output, but this I'll say is to be continued. All right, we'll get to this in later videos. Other things that you can do that will not result in a real number output, but for right now I'm only focused on the fact that you cannot divide by zero. All right, so looking at my function here, finally back to the example, I have f of x equals, or the value of f at x equals 3 times x squared plus 2. So one thing I'm noticing is there are no denominators with variables. Right. Right, that's one. So again, in this example here, this particular function, I'm noticing that there are no denominators with a variable. Right, with a value of x. There are technically denominators of 1. You can throw 3x squared over 1, 2 over 1, but again, there are no denominators with a variable. And that's all I'm really focusing on right here. So because there are no denominators with a variable, I can replace x with any real number, and the output it corresponds to will also be a real number. I won't end up with, we'll talk about this in future videos, I won't end up with imaginary outputs, not any non-real outputs. And you can test it out, try a few examples, and I've mentioned before in previous videos, a few examples doesn't prove anything, just gives you a rough idea as to whether or not what you're doing is good. So like 3 times 0 squared, if I input 0, I'd get the output of 2, which is real. If I input 1.5, I'd get an output that's real. If I input the square root of 2, I'd get an output that's real. I input pi, I'd get an output that's real. Because there are no denominators with a variable here, in this expression I'm not going to be dividing by 0 ever, and every single output will also be a real number. So because of this, I will state that the domain, so because of this, I will state that the domain of this function f, so the domain of the function called f is, now you can do this a couple ways. Now because the domain has infinitely many numbers in it, it's all real numbers, every real number, you might see a couple ways this is expressed. One is with something called set builder notation, where I write a little curly brace, and my input variable, my independent variable, is called x, so it's all x's such that, and then a little bar or a little colon, maybe sometimes you'll see a little colon, 2 dots. But the domain consists of all values of x I want, as long as, and then over here after the bar, a little description of those values of x. Well, I just said, we can replace x with anything. So x is, real, right? X is any real number, or you could write out the word x is any real number, or all real numbers are can be x. But this is called set builder notation right here. Or, okay, you could also have written this in what's called interval notation, where, and again, I've put out a video on interval notation before if you want to look that up. I'm not going to really go into that much depth. So you put a left endpoint and a right endpoint, but there is no lowest endpoint. There is no lowest value, right? Where the values of x I can plug in are anything. So if I plug in -1,000, you can plug in -1,000,000, -1,billion, Googleplex, and this will still give me a real number output. So those numbers still belong in the domain. So to indicate that there's no lowest value in the domain, I put -infinity. Right? Again, that's a concept. That's not an actual number. It's a concept, meaning that there's no lowest value in the domain. And then a comma, and then the right endpoint. So all the numbers for the until you can go as low as you wish, all until, and then is there a highest value in the domain, a largest number I can plug in? Well, no. If I plug in 1,000, I could also plug in 1,001. If I plug in 1,000,000, I can also plug in 1,000,001. A billion, I can plug in a Googleplex, a Googleplex plus 1. You can plug in whatever you want. So to indicate that there's no largest value in the domain, the symbol positive infinity, or just the infinity symbols used. And then these left endpoint and right endpoint, low endpoint, high endpoint of an interval are capped off with either a parenthesis or a square bracket. And a parenthesis means that the lowest endpoint or the highest endpoint do not belong to the set, which you're going to do with infinities. Right? Infinity and negative infinity, as I mentioned, are not numbers. Right? These are concepts. So because these are not numbers, right, they don't actually belong to the set. Right? So this is the interval you would use to indicate that I'm looking at all real numbers. I can use any real number I wish, plug in anything I want for x, and get a real output. Okay, great. And so yeah, either one of these is fine. All right, and that's the answer to the question, right? That's what's being asked for here. So the domain of this function is all real numbers. Anything I want is allowed to be plugged in for the input. Okay, so that's just one simple example there, no denominators with a variable. Now my next one, doing the same thing, I'm asked to find the domain of this function. Now this function has a new name, and it's a function called h, and I'm asked to state the domain of that, what's allowed to be plugged in for x, what values of the input, what real values of the input correspond to real outputs. And so let's take a look at this. Alright, so if you look at this function here, we have h of x equals, and then we have this rational expression, a fraction, with x plus 1 in the numerator, and then in the denominator, divided by x minus 3. So this time I am noticing there's an expression with a variable in a denominator. And I don't care for that. I mean, it's fine. You can have the expression with a variable in a denominator. It's just remember, denominators can never be 0. If I divide by 0, as I mentioned, that does not yield a real output. All right. So the question is now, when is that denominator going to be equal to 0? So when is x minus 3 equal to 0? All right, now that's a simple linear polynomial equation. When is the denominator of x minus 3 equal to 0? Simply when, just adding 3 to both sides. The answer is when x equals 3. All right, so this value here then. All right, this isn't the answer. I'm just bubbling it so I can point it out. Okay, so this value here, 3, this is not in the domain of this function. Not in the domain of h, right, function h. Because if I use this value, if I make that my input, my argument, right, replace x with 3, I would not have a real output. Right? I'd have 4 divided by 0, and that is undefined. Right? That is not a real value. And that seems to be the only restriction here. Right? That is the only value that makes me divide by 0. That doesn't correspond. So that's the only value for an input that wouldn't correspond to a real number output. Everything else would be fine. Go ahead and try some. Replace x with 4, 5, 10, 1,000, 1/5, -7, whatever you want, as long as it's not 3. And you'll see that you'll end up with some real value, right? Some real number value output. Okay, so indicate that this way then, right? From all this, then the domain of this function so the domain of h, and you could write it in this set builder notation, right? It's a set of all values of x, right? My independent variable is again x here, so it's all values of x such that, or as long as, and then the condition on there, it's any real value x as long as x is not, right, is not 3. And that's the only restriction. And I'd close the set there. Alright, so this is saying I can replace x with any real value I wish as long as it's not 3. Alright, so I can replace it with, like I said, 4, 5, 7, a million, whatever you want, as long as it's not 3. Or, if you wanted to do that interval notation, now, interval notation here is a little trickier because there are actually two pieces of, if you think about the real number line, right, here's the real number line. Let's put real numbers, okay? And let's say this real number line represents possible values of x, values of my input that I can replace x with. So, I got 0 in the middle and positives to the right, negatives to the left. Now the number 3 is mentioned, right? So say 3 would be to the right of 0. And what we're saying is, I can use anything but 3. Alright, so I can let's exclude 3. So I like to put like an open point above a number when it's not included. Alright, 3 is not included, so there's nothing there. But then everything else, right? All the numbers to the left of 3 belong in the domain. All the numbers to the right of 3 belong in the domain. So that there's like a graph of the domain, if you will. So when you're drawing intervals, when you're writing out intervals, you write them. You write one interval for each piece of the domain, each piece of the set. So you notice here how there's like a break in the set. I can't just say, like I did in the last example, oh, there's no lowest value, so I'll start at negative infinity. Oh, and there's no highest value, so I'll go to positive infinity. Right? Because if I do that again, if I did this, this would imply that everything is in the domain, but 3 is not. So this is no good, the negative infinity to infinity thing that I had like in the last example, because there is a break, right? There is a break in the graph, right here. There's a break in the domain. So really what I have here are two separate pieces. Right, two separate intervals. So here's one interval to the left of 3, and then a break in the graph, and then another interval to the right of 3. Alright, so when you're writing out the solution, when you're writing out a set in interval notation, if there are breaks in it, you must account for that. You must write an interval for each piece that's separated by those breaks. So for the first piece here to the left of 3, yes, there is no lowest value in the domain, right? You pick -1,000, I say -1,000,000. You say -1,000,000 is the lowest, I say -1,000,000,000, right? You keep going with that. So as I mentioned in the last example, the way to indicate that there's no lowest value in the domain there is, right, -infinity, comma, and then this is everything from, from the far left here, from -infinity up until, and then up until the break, right? What's the right end of this interval here? It's at 3. Right? So we're going every value up until 3, but not including 3. Right? We said 3 is not in the domain. So just like last example, I'm putting parentheses on these to cap them off. So this is basically saying x can be any value less than 3. That's this piece of the graph over here of the domain. Any value less than 3, just not 3 itself. And then there's a fancy symbol you'll come across. It's not really that fancy, but this when you have the multiple pieces like this, when I'm picking an input, I can pick a value from the left of 3 or from the right of 3. Less than 3 or greater than 3. And a symbol to indicate that in interval notation or set notation is this U shape. Okay, it's a big U, and its symbol is for the in union with. Right, this is the union symbol, and really it's just a symbol representing the word or. So I can pick a number from this set or this other set I'm about to write, the right side of 3. So this other piece, the left end, it begins at 3, and there is no right end. The low end begins at 3, and the high end, there is no high end. There is no largest value in the set, so I indicate that with an infinity, a positive infinity symbol. And again, 3 is not in the set, so parentheses, and infinity is not a number, so parentheses on that again. So if you would like to indicate this domain with interval notation, this is how you'd have to do it. There are 2 intervals to draw. There are 2 intervals to write because there is a break in the graph. There is a break in the domain at 3. Breaking the real number line up into 2 separate pieces, so I need 2 intervals. Okay, so again, if there'll be other videos up, I'm sure, on interval notation and whatnot. This is a very brief statement about the union symbol. Okay, all right, and that's it for that. Right, I was only asked to state the domain of this function. I can plug in anything I wish. I can use anything I want for my input, except 3. Simple as that. All right. Now, these past 2 examples were just, I simply, gave you an equation with no context. They weren't involved in a real-world scenario. It wasn't part of a word problem or an application problem. So when I thought about the domain, I just said it's any real number I want as long as I don't divide by 0, right? And that's a good way to think about when you first start off trying to state the domain of a function. What makes me divide by 0? But very often you come across equations that are actually related to a real-world problem that actually have context. So you must pay attention to context, right? When you're asked to state the domain of a function. So here I have an example of an equation that has some context. The function, now this is a little different. My input, my independent variable, my input is this r, and the dependent variable is this a of r. So I have the function capital A at r is equal to pi. Right now, remember, pi is approximately 3.14159, so on, so on, so on. Right, it's one of those irrational numbers. So this is the number pi times r squared. All right, so here's an equation. A of r equals pi r squared. Gives the area of a circle A, right? So this A of r represents the area of a circle as a function of the radius of the circle r. Hopefully you remember what that meant. When I say A is a function of r, that means every value of r I use corresponds to only one possible value of A, right? The question here is now, what is the domain of the function? So there is context here. All right. Normally, if I just gave this equation without all the words around it and said, what's the domain, right? I'd say, oh, it's all real numbers because, this pi times r squared, there's no denominator with a variable. I'm not going to be dividing by 0 ever. So I would say it's all real numbers, right? But that's not true. The context here is circles, right? We're talking about circles, and areas of circles, right? And you know, you know what a circle looks like. Now this isn't going to be perfect. I apologize. I don't have a. I should have probably had a compass on me, but there's a circle, right? And you have a center of the circle, and every point on the circle is the same distance from the center, and that distance was called the radius, right? Radius of the circle. And then the area, right, is the amount of space taken up, right? Okay, and but the radius is a length, right? So when they're mentioning radius of a circle, this is a length. And the length of a segment is a positive value. Is a positive quantity. All right, because it doesn't make sense to have negative length. All right, because if I said, let's draw a picture, with a radius of, 1 centimeter or something, right? I could do that. That's a positive length. So here's here's 1 centimeter right there. Pull a ruler, and then a circle with a radius of 1 centimeter. Again, very just eyeballing this. I should have brought a compass, but there's a circle with a radius of 1 centimeter, right? And I could do that with any positive length, a radius of 3 centimeters, 4 centimeters, 5 inches. I could draw a circle if I give you a radius that is any positive length. So my input could be any positive value, right? R can be any positive value. Well, what about negative values, right? Does it make, what does it mean if I say draw a circle with a radius of -2, -2 centimeters? What does that mean, right? How can a radius be negative? How can a length be a negative quantity, right? You never see that on a ruler. You don't see negative lengths, right? There's no negative lengths marked off on a ruler, so I can't see how that could be done. And additionally, too, what about 0? I was talking about positive. I talked about negative. What about 0? If I said draw a circle, okay, draw a circle with a radius of 0, that would simply be a point. Right? There is no length coming off of this point. So there you go. A single point is a circle, and I'll put this loosely, with a radius equal to 0 units long, 0 centimeters, 0 miles. It doesn't matter. 0 of any unit length is going to be just a single dot. So I mean, this really, I wouldn't really call this a circle. Now I guess technically you could say it's a circle with an area of 0 square units, right? It takes up no space whatsoever. This one would take up pi square units, so I replace pi square centimeters if you want to write that, and write the area. The area at 1 centimeter would be pi, square centimeters, right? Because remember, it's radius squared. You do centimeters times centimeters, or square centimeters, centimeters squared. And this one could, you could say that this has an area of 0 square units, but But really, if it's taking up no space, I wouldn't consider it a circle. And I know I've seen some texts where they would consider it a circle technically by definition, and others where it's not considered a circle. All right, so I guess it's really up to you. But really, this is key though. There is no negative radius. Right. So that makes all the difference, right? You got to pay attention to the context. Does it actually? Does the equation actually have meaning? Right? Does the function given to you have some sort of real world meaning? Right? Oop, can't spell. Right. Because those first two examples I gave, with like this function here, what is this even related to? I just gave a function and asked for its domain. It's not related to anything, but this one is. Right? It's related to circles. Okay. So now that I've said all that, we can finally state the domain. So the domain of this area function, this a here, and like I said before, I'm going to do it both ways with the set builder notation. I can use any r I wish, right? Again, the independent variable this time is r. My input is r. I can plug in any value of r I want, and as long as it's not negative. Now, me personally, I'm going to say as long as it's not negative or 0. So as long as it's positive. So as long as r is positive, right, you can write out the words r is positive, or as long as r is greater than 0. And if you want to, you can say greater than or equal to 0 if you consider a dot a circle by definition. Fine. But this is great. All right. It's the domain of this function in the context of what I'm saying, right? In the context of what it means. Like I said earlier, if that weren't there, right, if none of these words were there, and I just gave you this equation and said, what's the domain? Then you would say it's all real numbers. You can plug in whatever you want for r because they'll never be divided by 0. But because it's about circles, radius can't be negative. I got to say the domain is just values of r that are positive, right? You can make the radius as big as you want and draw a circle as big as you want and find its area. All right, and if you're doing interval notation, again, now this is the left end, the lowest this gets is down to I don't have 0 included, but that's the left end, right? The lowest it gets to is anything up to 0. And then it's then the value of r is anything greater than 0. So you can make the radius as large as you wish, right? You could draw a circle as large as you wish, right? As big as the universe if you wanted to. I mean, you probably wouldn't be able to do that practically, but you could. It's not impossible, but and then I'm saying that a radius of 0 isn't really a circle. Right? Again, a radius of 0 is a dot. Now, if you'd like to put the square bracket on here, say that a dot is technically a circle, that's also fine. I'm just making sure that we're not including negatives, okay? And then infinity, always a parentheses on infinity. All right. So just be careful. Now, when you come across a word problem, an application problem, and then you have an equation involved, just that equation will have some meaning. You'll have some context, and given that context, if asked to state the domain, you're going to have to be able to you're going to have to plug in values. You're going to have to use inputs that actually make sense, in the context of the problem. So just be careful with that when asked about that. All right. So that's just a few examples today. Just some pretty simple ones, I feel. And we only talked about the fact that you're only looking out for am I ever dividing by 0? All right. If you're not dividing by 0, you're fine, and you get real outputs, and that'll be added to later. I've mentioned before there will be other scenarios where your output will not be a real number, and that's for future videos. Okay. So as always, I like to say at the end of these, try your best, do the best you can to get the material, understand the material on your own before you go looking for help. read the material, of course. Read through the author's examples. Perhaps even try to work out some of the examples before you read how the author did them, and then go back and read what the author did and see how you compare. Maybe you can learn from your mistakes there. Of course, practice problems, practice exercises, look up solutions where they're available to check yourself. And don't just give up after the first couple of attempts. Don't give up so easily. If after several attempts at a problem you're still not getting it, it's still not clicking for you, perhaps you should read the material again, maybe even a third time, because who knows, maybe that second or third read through, if you read through a little more carefully, you might just catch something, or something might click in your mind that you didn't see the first time through, and it'll make the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, still not working out for you, still not getting it, well, then it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in your class that you know knows the material well and is willing to help. Look for supplemental materials online. There's lots of stuff out there on everything. Look for videos on the subject, such as this one, or plenty of other videos out there better than this one. I assure you can find them. But just keep at it. Stay persistent. Keep practicing. Don't give up. And also try to have a positive attitude. That can make all the difference. Go into this with an open mind, thinking I'm going to enjoy learning this. I'm going to actually take something away from this. I'm going to have a good time with this. Have a positive attitude, because if you go in thinking I hate this, I've always hated math, I've never been good at it, you're probably going to continue to hate it. It's a mindset. It's amazing the difference a little change in attitude can make. So stay persistent, keep practicing, stay positive, and I just know you'll get it. You'll get it eventually. I know you can. And thank you for watching.